Okay, welcome to week 4 review session for Engineering 210 Circuits class. Today we're going to be talking about three main things, being mesh current, superposition, and Thevenin equivalence. I have been told that these will probably be on your quiz. I don't exactly know how it'll be laid out because you only have two questions on the quiz, but these are kind of the topics I was told to focus on for this week. So, I'll get started with, I'll give a brief overview of superposition first. The general idea with superposition is that you can look at the circuit as basically you can look at the sources separately from each other and they still add up to what you want. The idea here is that resistive circuits are linear, if you know what that means in math terms, meaning like if I have something here and something here, then if you add them together, it's the same as if they were both happening at the same time. That's what it means whenever you see superposition. So basically, the idea with that, though, is that we can look at, let's say this circuit was like bigger. I don't know, you had another resistor there. If you wanted to find the total voltage across this resistor, you could look at this circuit in two forms. One where you have the voltage source and no current source, and one where you have the current source but no voltage source. And if you find your like V prime and V prime prime, as it's been called in class or on your homework, and then you add them together, then you'll find that that original V you were looking for is going to equal to that V prime plus V prime prime. This can be useful if like, I don't know, the circuit's really complicated. Frankly, you don't really have to do this ever because node voltage and mesh current are powerful enough that this is just kind of a neat trick for the terms of this class. But like, it's good to know, and I think there might be a question on it. So if the question asks you explicitly to do that, then you have to do that. I'll do a practice problem on this, I think. I think I had one here somewhere. Yeah, I'll do a practice problem on this, but this one's pretty straightforward. The idea is always just, okay, turn on one source at a time, solve the circuit, and then do it again for the other sources, and then add your answers together. One thing I will note is when you are doing this, you have to neutralize the other sources. So neutralizing sources, because you'll be doing this a bit, you'll also be doing this for Thevenin equivalence. So a good way to remember what you do is, so for voltage sources, a voltage source goes to a wire because wire is 0 volts, right? There's a 0 volt difference across a wire. So if you had a 0 volt source, it would just be a wire. So you're going from some voltage source to no voltage source. Likewise, a current source provides some current, it makes a current flow, and the opposite of some current is no current. So a current source, when neutralized, would go to an open circuit. So when you have to do this in the class, remember it that way. Okay, next up we have Thevenin equivalence. So the idea with the Thevenin equivalent is that if you have, where's where's the one I wanted to look at? Oh, it was all like, yeah. Yeah. So if we have like a circuit that's pretty complicated, um, let's say I'm not going to fill in any values, I'll do practice problems later. And we wanted to connect this to some other circuit over here, right? And this is the circuit we really care about. This is just something we're attaching to it. Then what we'd want to do is figure out, okay, from the perspective of these two terminals, what does everything over to the right look like? And what you can do for resistive circuits is that you can basically, or for most circuits, you'll see later in the class, you can turn this into something that is effectively the same, where it just looks like this. So all of this behavior over here can end up being simplified into just a voltage source and a resistor. It can also be turned into a current source and a resistor just by a source transform as well. But that's the idea with Thevenin equivalence. The way you do this is, so let's say we wanted to find, or I should have erased all of that. And what we'll call this is VTH and RTH. So VTH, very simply, is going to be the voltage. In this case, it would be the voltage between A and B. So it's just the voltage between the two terminals that you're looking at. RTH, there's two ways you can look at it. It's either going to be the equivalent resistance of the circuit when all sources are neutralized, or you can think of it as if you were to put a wire here, what would be the current that flows here? So, or, and basically based on, so if we call this I short circuit, then it also equals the VTH over that short circuit current. Those are the two ways you can do it. If you want to find the short circuit current, basically you'd have to solve the circuit twice. So you'd solve the circuit once without this short there, and that's how you get your Thevenin voltage, which is from here to here. And then if you want to find the short circuit current, you would basically insert a wire here and then solve the circuit again and figure out what that current is. And then to find your RTH, you would divide the two. Usually though, you only really have to do this one if there's like a dependent source in here, or if it's like, I don't know, it happens occasionally, but most of the time you can just neutralize all the sources and then combine all the resistors. So like in this case, you would make this a short, this an open circuit, and then let's see, you'd have it would go to something like uh that, that, but it's broken there, so we don't actually care about that branch. That, that, and then we combine all these resistors. So these two would be added together, and then these two, and then so those two would get added together, and you'd have uh like this. And then these two are in parallel from the perspective of these nodes, so that would go down to one resistor, and then that would be your RTH. So I'll do that on a practice problem later. Last but not least, we're going to talk about mesh current. So mesh current, of course, is basically like the opposite of node voltage. So if node voltage is looking at the current at each node, mesh current is looking at the voltages around each loop. So if we have some big circuit with a lot of components, and we want to find out different things about this circuit, a lot of information here. We don't really care about what's going on in, like, we don't want to have to deal with finding all this on our own. So what we do is we kind of make up some variable current that's flowing in a circle around each loop. These currents like don't exactly exist. You're kind of making them up as variables in order to help you solve the problem. But the idea here is that you do a KVL loop or a KVL equation around each loop. So that's looking at the voltages. So like for this first loop, if this was like 3 ohms and this was 2 volts or something, right? You'd go back to your passive sign convention for figuring out the direction of the voltage. And basically, it'll all make more sense when I do practice problems, of course. But like you do, okay, 3 ohms times that I1, because that's going to be the voltage across that resistor. And then here plus 2 volts because the current is in the direction of the voltage drop equals 0. And then if you repeat that for all the other loops, then you'll end up with 4 equations and 4 unknowns, and you can solve for all your currents. And then once you've solved for all your currents, you like basically have your answer. So hopefully you've all seen these topics, you all did the homework, so you should have a starting point, and I will spend the next 45 minutes doing practice problems. Okay, so I'll start with some kind of basic node voltage ones, or not node, some basic mesh current ones. So actually, I'll copy over this circuit that I just did. Um, and actually give it values, because that is one of the questions I have here. Yeah. So if we look at this and we actually give it values, it would be in the question I was given 40 ohms, 50 volts, 5 ohms, 50 ohms, 10 IX, um, 10 ohms, and 4 amps. Okay, so some key things I will say is always make, just like for your own sanity, always make all the currents, so all your currents, like your INs, go in the same direction, because it'll just make your life easier. The other thing is that if there is a current source, then it tells you what the current is. Like, so don't try to write an equation. Don't try to use KVL, right? So what I mean by that here is that if you look at this rightmost loop, we've defined I4 as the current flowing around here in this direction. However, there is a current source pointing up here, which is telling you that along this branch, we have 4 amps flowing that way. Of course, since I said make them all go into the same direction, we're still going to call I4 going that way. But what that tells us, though, is that I4 is just going to be negative 4 amps, because it's just, we've defined I4 as going in one direction. The current source is telling us it's going in the other direction, so it's just the opposite. And then for the other loops, though, um, we can just do our KVL equations. And let's say for this question, it was asking us to find V2, or write all equations to find V2. So we have I4. I just did that because I wanted to emphasize this, but now I'll start with I1. So for I1, around this loop, we're going to have 40 ohms times I1 plus 2 volts equals 0. Again, that's 2 volts because the voltage drop is in the direction of current. By our passive sign convention, that is positive. Next up, going around I2, now we're going to have that 2 volts, or that 2 volts being negative. So negative 2 volts plus 5 times I2 from that top resistor. And then this is what you're going to have to be doing most of the time. When you have a resistor that's between two sections, you have to look at, okay, from the perspective of this loop, right, we're going to call that I2 be positive. So the actual current flowing through here, right, we have, if we're basically saying, okay, for the purpose of this loop, we're imagining the current is flowing down because this is going like this. So what we have here is I2 going positive direction and then I3 going against it. So if we want to think about the overall current here, it would be those plus each other. So it would be I2 minus I3, right? Because this one is opposing it. So that would actually be our current for this resistor. That resistor has a value of 50 ohms. So it's going to be 50 ohms times I2 minus I3. Then in the next equation, and then all of that equals 0. And for I3, it's going to be the other way around. So we still have that same 50 ohms, but now, since we're in the perspective of I3, now we're thinking, okay, I3 is positive, I2 is negative, because we're in the I3 equation. So now it's going to be I3 minus I2 as the total current going through this resistor. Again, if you look at each of these terms in this equation, all of these are going to evaluate to a voltage because V equals IR. So always double check that your terms are all evaluating to voltages. So you either have a voltage here or you have a resistance times a current, and that equals a voltage. And as we can see here, we have that. For this 10Ix, is this going to be positive or negative? Well, let's look. We have the current going this way, and the voltage drop is not in the direction of the current. So that means it's a negative 10Ix. Even though it has a current here, it's telling us it's a voltage source, so it's a voltage. So this is a voltage. You can think of this 10 as having units of volts per amps, and then when you multiply that by your current, the amps will cancel and you'll be left with some voltage. Um, and then we have that 10 ohm resistor on the right, so it's going to be plus 10, and it's going to be I3 minus I4. If you wanted to, you could just fill this in with 4 amps and it'd be fine, but for the purpose of the equation, I'll leave it in variable form. So right now we have 4 equations and 5 unknowns because we still have this Ix. So we have to write an equation for Ix. So for Ix, very simply, if we look at Ix, right? Ix is going this way, and we know that, and we've defined our I2 as going this way, so you can just say Ix equals negative I2. And that's nice and easy. And then last but not least, write all equations to find V2. Okay, what's V2 here? Well, we already found V2 earlier. It's this term or this term, whatever you want to look at, right? So V2 then, oh, actually though, since V2 is defined as having the positive on top and the negative on bottom, that would happen from a current flowing in this direction. If you think about it, right, when you have a current flowing through a resistor, the resistor is always going to dissipate power, and that means it has like a positive voltage, and that means the voltage drop will be in the same direction as the current. Think about your passive sign convention. But basically, what that means is that we are going to be thinking of I2 as being the positive one here and I3 being the negative one. So V2 is going to be equal to that 50 ohms times I2 minus I3. And then this would be your answer. So that's kind of how you approach these questions. Okay. And I'll do one more, just kind of the same thing, node voltage or mesh current. Yeah. And this one has more of those resistors in the middle, and that'll be a good example. Yeah. Oop. Okay. Minus a resistor here. Okay, I think I got everything. Yeah. So then let's say it was asking us to find this voltage here on the 4 ohm resistor. So write all equations, write all like mesh current equations to find V 4 ohms. And this is the V 4 ohms. So since we're using mesh current, we have to start by defining all of our currents. So I personally like to do them all clockwise. It doesn't matter, just pick one and stick with it though. So for me, that means I'd do I1, I2, I3, I4, and I5. It doesn't really matter what you label as what, as long as you're consistent in your equations. So if we wanted to solve this circuit, we would just need to write out our five mesh current equations and write out an equation for what this Vx is, and then plug it into a calculator and it can solve it. Because you will have six equations and six unknowns. So let's write out all those equations. So first, for I1, oh, it's that case I mentioned earlier, right? We have a current source and it's on a loop. So what it's telling us is that through this, we have 3 amps flowing, right? So if we've defined our I1 as going this way, then that means here we have negative 3 amps. Because if we think of it, right, this is I1, it overlaps with this current source, so I1 has to be defined by that current source. So I1 is very simply just negative 3 amps. For I2, we no longer have a current source, so we have to, actually do the thing here, which is unfortunate. Oh, I missed, oh, okay, wait. I forgot to define IX. As you can see, this dependent current source is defined by IX. IX is here. So for I2, this is a colon, not an equal sign. We're going to have, just as before, 4 ohms times here, since we're in the I2 loop, I2 is positive. So it's going to be I2 minus I1, right? Because again, we have I2 going up, I1 going down, because that's how they're defined. So we have I2 minus I1. That's our first one. And then plus with that 6 ohm resistor on the top, it's going to be 6 times I2 minus I5 for the exact same reason. Next up is going to be plus 10 times I2 minus I3. And then with this dependent voltage source, since the voltage drop is in the direction of I2, we are going to label it as positive. So plus 2Vx, and that all equals 0 because that's the last component. One thing you will notice is if you're doing it right, you are always going to have the loop you are currently in as the first term. So just always do that. It's very straightforward. Um, Next up for I3, we got now the voltage source is going to be negative because it's coming in the other direction. So minus 2Vx plus 10 I3 minus I2. Again, you'll notice that this is the opposite of this, right? Then with that 8 ohm voltage, with that 8 ohm resistor, it'll be plus 8 I3 minus I5, and then plus 2 times I3 minus I4, and all that equals 0. Last but not least, or actually not at all last, we're just keeping on going. We see I4 here. We have the same situation as the first one, where it is just given to us because we have a current source. Again, because they're in opposite directions, it'll be negative, but I4 is just going to be negative 3IX. Now, almost last, we have I5. It's 5, sorry. And I'll start with that voltage source. The voltage source, again, the drop is in the direction of current, so we're going to call this positive. So we have a positive 12 volts. And then with those two resistors, it's going to be the opposite of what we saw earlier. So now it'll be plus 8 times I5 minus I3 plus 6 times I5 minus I2. And that equals 0. Then we need to define our two things that are used in our dependent sources very quickly. So IX, we'll call it, yeah, IX. Since it's going down between two branches, it's going to have to be the sum of these two currents in some way, or this is the difference. Since it's defined as going down, we're going to use I1 as positive because that's the one that agrees with it. So we will see that IX is I1 minus I2. Then for Vx, okay, it has positive on the left and negative on the right, which means that it's kind of expecting current to be flowing to the right through it. That means I3 is going to be the positive one and I5 is going to be the negative one. And we're just going to end up writing that same term we saw earlier, which is that 8. So we saw it right here. So it's 8 times I3 minus I5. And now we have our 7 equations, 7 unknowns, and you could plug this all into a calculator. But hopefully, as you can see, it's kind of a straightforward process. You just kind of go around the loop, write your equation. If there's a current source, it's easy for you and it tells you. But but yeah, very cool. Okay, now I'm going to get into some of the other topics that we're covering here. So I'll do a source superposition question. So the reason that I said like I kind of feel like superposition is something you don't need to remember that much is because in this case, like me personally, I would just do node voltage here because it's like straightforward. It's one equation and you could find Vx. But for this question, it is explicitly asking you use superposition to find the power of the 6 ohm resistor. Um, if you remember, that is going to be equal to IV, which is equal to V squared over R. So if you just find V squared, then we can find, or in this case, it'll be Vx because that's what's labeled on the diagram. But if we can find Vx, then we can find our our power. So if we're using superposition, there's going to be two different versions of the circuit we have to solve. So we have our first one with the voltage source and the current source open because it has no current. And then we have the one with the current source, but the voltage source shorted because there is a 0 volt difference between its two terminals. I'll fill in all these values. And if we remember, right, we want to find our Vx prime and our Vx prime prime. And then when we add those two together, we will get our answer. So how do we go about this? So for this first one, you can look at, okay, there's no current flowing through this part of the circuit. It's broken. So we can just completely ignore that, which is very nice. Then we just have a voltage source and two resistors. So we can just do a voltage divider, right? So Vx prime is going to be equal to that voltage source times that 6 ohms over the total resistance, which is 6 plus 3. If you look at this, this is going to be 12 times 2/3, which gets you 8 volts, right? So that's our Vx prime. Then on the right here, it's a bit more involved. If you were to look at this, this could also be drawn with like these two in parallel. Yeah. So this could also be drawn like this, and it wouldn't change any of the connections. That just makes it a bit more clear that they're in parallel. So one thing that's nice here is since we only want to find the voltage of things in parallel is the same because it's the same voltage here and the same voltage here. But what that also means is after you combine the two resistors, the voltage will still be the same with like that combined resistor. So if we want to do that, what's 3 and 6 in parallel? So it's going to be 3 times 6 over 3 plus 6. So times. It's going to be 18 over 9, which is 2 ohms. So what we end up with then is 2 ohms, 2 ohms, and 2 amps. Uh, yeah. And then we will get 4 volts, but like that, right? Since the current is going that way, that's going to be the direction. So really what we have here is we have negative 4 volts. Then if we want to find our ultimate answer of Vx, it would be Vx prime plus Vx prime prime, which is going to be 8 plus minus 4, and that gets us 4 volts. And finally, if we want to find the power of that 6 ohm resistor, it'll be 4 squared over 6, which is 16 over 6 which is about 2.667 watts. Let me close Discord. Okay. Um, yeah. So another way you could have done the one with the current source is you can also use mesh current for that, and that would be also straightforward. I'll go over that real quick because that can be a bit more easy to see. So we could have also done this as we're trying to find this. We have 6 ohms, 2 ohms, 3 ohms, 2 amps. And then if this is our I1 and our I2, we know our I2 is very straightforward, just going to be 2 amps because of the current source. And then for I1, we would have 3 ohms times I1 plus 6 ohms times I1 minus I2 equals 0. And then we can plug in our 2 amps here and solve for I1. So it would be 3 I1 plus 6 I1 minus 6 times 2 equals 0. Solve that pretty straightforward. It'll be 12 over 9, I believe. Yeah, 12 over 9. So you get kind of 4/3 amps for I1. And then if you want to find that voltage, right, it'll be 6 times I1 minus I2. So 6 times 4/3 minus 2. And that will end up getting you that same answer of -4 volts. So this way might make a bit more sense if you got confused by the sign here or about the parallel stuff, but you end up getting the same answer. Okay, let's find another question that looks good for now. Um, yeah, we can do this one. Okay. So, uh, yeah, this is pretty similar, but kind of not quite the same. It's all one line. And then we have 3 ohms. So use superposition to find the power of the 3 ohm resistor. So again, very similar. We'll split it into 2 different versions of the circuit. For the first one, I'll do the current source being open. So we have like a open terminal here, resistor, 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 voltage source, and then all of these get connected down on the bottom. And we want to find the voltage across that 3 ohm resistor, right? So that's going to be our Vx prime. And I'll go through this real quick. So again, we basically just want to simplify those 2 resistors on the left, and then you can do a voltage divider. So if we look at that, um, yeah, if we look at that, um, if we want to combine these 2, it'll be 4 times 6 over 4 plus 6. It's going to be 24 over 10, which is 2.4 ohms. So then we have something like this, where we have 3 ohms and 2.4 ohms and 2 volts. And then if we do a voltage divider, it'll be the voltage of that 3 ohms is going to be 2 volts times 3 over 3 plus 2.4, which gets us, let's see if that's a nice number, 2 times calculator 3 over 3 plus 2.4 gets you like 10 ninths or 1.1111. And one thing to note is that this is actually kind of going to be negative based on the sign that I gave here, because the current will be flowing this way because of the way that the voltage source is facing. So this is a negative 1.11 volts. On the current side, so when we short that voltage source, but we leave the current source, when I draw those two little dots here, it's kind of just representing that there was a voltage source there, but no longer. So one good rule of thumb is that when you are actually, yeah, you can just combine all these resistors and then find the voltage because they're in parallel. But generally, if you're looking for the voltage or current through a component, you don't want to simplify it away. So like best practice here would probably be just combine these two and leave this one alone and then do mesh current. But for the sake of actually I'll just do that. Yeah. So in the same way you can combine those as we did last time. Exact same thing. Now we have 2.4 and we have 3 and 4 amps. If we do a mesh current, I1, I2, we're going to get that I1 equals 4 amps. And for I2, we have 2.4 times I2 minus I3 plus 3 I2. I don't know why I said I3. That should be I1. And that equals 0. However, we know what I1 is, so it's going to be 2.4 times 3 minus 2.4 I1. Or no, yeah. No, I did that backwards. 2.4 I2 minus 2.4 times 3 plus 3 I2 equals 0. And then we can find I2. What is it going to be? 5.4 I2 equals 2.4 times 3 is 77.2, I think. That feels right. Yeah. And then if we do 7.2 over 5.4, you get 1.33 or 4/3. So then if we want to find our Vx prime prime, which is what we were looking for, right? It's going to be just IR, which is going to be I2 times 3, which is going to be 4 volts, because this is 4/3 times 3, you know. And then last but not least, now that we have that voltage, we can find our Vx is going to be 4, or it's going to be minus 1.11111 plus 4, which will get us 2.88, kind of 2.889. And then if we want to find the power, it's going to be that squared over 3, which, ooh, I might have messed up somewhere. Where did I mess up? What's 4? Where did I mess up? Um, this is not supposed to be that. Oh, because this is, wait. Oh, yeah, yeah, yeah. That's what I messed up. Okay, I see. I said that I1 is 4, but then I plugged in 3 for it because I'm silly. So this is supposed to be 4, and then 2.4 times 4 is going to get us 9.6. Yeah. And then if we do 9.6 over 5.4, we get, yeah, 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 yeah. Okay. 1.77 amps. And then if we do this, we get different number, 5.33 volts. And then we do this. Yeah, okay. There we go. So we get 4.22 And then it's going to be 4.222 squared over the 3 ohms, and that will get us 5.94 watts. So again, split the circuit into versions where only one of the sources is activated and all the other ones are deactivated, whether that's shorting or opening them. Get your voltages that you want, and then add them together, and then that's your answer. Or then you have to like turn that into your answer. Okay. Next up, I'll do some Thevenin equivalent questions. Thevenin equivalent has like kind of similar, you have to know what you're doing with shorting sources and such, but it's not too bad in my opinion. Mm, yeah. So start with this one. Okay, so it's find the Thevenin equivalent with respect to terminals A and B. So for this, what we need to do first is find the VTH. So VTH, which is going to be equal to VAB. So that means we need to find the voltage between here and here, right? And if we look, there's not any current flowing this way. And since V equals IR, if there is no I, then there is no voltage drop. So that means that this voltage is the same as this voltage. So really, we can ignore this for now, for the purposes of finding the voltage. And then really, we just need to find the voltage here between these points. And to do that, I'm going to use node voltage because I like node voltage. So if I call this V1 and this 0 volts, then let's see what we have. We have, so at V1, going to the left, we have V1 minus 30 over 5. Going down, we have V1 minus 0 over 3. And then coming in from that left part, we have minus 2 amps equals 0. Multiply everything by 15. You're going to get 3V1 minus 90 plus 5V1 minus 30 equals 0. Add everything up. 8V1 equals 120, so V1 equals 120 over 8. I should be able to do that in my head, but I don't want to. It's just 15 volts. So we have V1, and so that V1 is going to be our VTH. Wow, we did it. Next up, we have to find that VR or that RTH. So I'm going to do this with the nice method of canceling out all the sources and finding the whole circuit's equivalent resistance. Oh, that looks disgusting. There we go. So there was the voltage source there, but we've shorted it. Okay, so we have 5 ohms, 6 ohms, and 3 ohms. We no longer can ignore the 6 ohms because it is there from the perspective of A and B, right? We're looking at the resistance from that point looking to the left. So first off, I'll redraw the circuit a bit just so you can see all the components have stayed connected in the same way, but this way it'll look a bit more clear as to what you need to do, right? Okay, now we see, okay, we have two things very clearly in parallel, and then once we combine these, it'll be in series with this, so we can just do that. So we got 5 ohms and 3 ohms and 6 ohms. So first off, I'll combine the 5 and the 3. 5 times 3 over 5 plus 3. That's going to be 15 over 8, which is not a nice number, so I will just leave it written as 15 over 8. So now we have A and B. We have 15 over 8, and we have 6. So our final equivalent resistance is going to be 15 over 8, which is a number plus 6, and we get 7.875 ohms. And that is our RTH. And then last but not least, we have to actually draw the Thevenin equivalent circuit, which, as I went over earlier, is just a voltage source with the resistor. And we call this A, and we call this B. So this is 7.875 ohms, and this is 15 volts, and that would be your final answer. So pretty straightforward. You find the voltage, and then you remove all of the voltage sources and current sources, and you find the equivalent resistance, and then that's your answer. Okay. Okay, this is a good one here. Yeah, I'll do this one next. Because this one has something that could be a bit tricky. Okay, so same question, find the Thevenin equivalent with respect to A and B. So again, when you're finding the voltage, since there's no current flowing through this branch, you can ignore the 2 ohm. We do have to pay attention to it once we get to finding that resistance though. So to start though, I'll cross this out for now. And again, I'm going to do the same thing. So we can say node voltage here, and this is 0 volts. And then we just do a node voltage equation and try to find V1. So that's going to be V1 minus 16 over 4 plus V1 minus 0 over 6 plus V1 minus 2 over 3 equals 0. If we multiply by 12, if we multiply by 12, we'll get 3V1 minus 48 plus 2V1 plus 4V1 minus 8 equals 0. If we add all the V1s up, you get 4 plus 2 plus 3 is 9V1, I believe. And that will equal 56. Is that right? Yeah. So then V1 equals 6.22 volts, roughly. Now that we have that, we can't just say that V1 is equal to VAB this time because B is no longer, if we look at the last question, right, our B was connected to what we defined as 0 volts, whereas this time it is not. However, we do know what this voltage is because there's just a voltage source here. If we're at 0 volts at that point and then we have a 2-volt voltage source, then it's just going to go up 2 volts from 0, which gets us 2 volts, right? So our VB is 0. So if we want to write that out explicitly, we know VAB equals VA minus VB, which is going to be V1 minus 2 volts, which gets us 6.22 minus 2, which is just 4.22 volts, and that would be our VTH. Next up, we got to do our resistance. And now we do have to care about that resistor on the branch there. And again, this is where you have to really think about, okay, this is from the perspective of A and B. So we're looking at, okay, if I were to send current in through A, where could it go to get back to B? 4 ohms. Okay, so first off, we can combine these two in parallel. So let's do that. If we look at that, it's the same numbers as last time. It's just going to be 2.4. So this will get turned into 2.4 ohms, 3 ohms, and 2 ohms. Hopefully you can see I've redrawn this, but all the connections are still the same. This just looks a bit more clear. And this is A and B. Next up, okay, we can't combine this with anything yet because it's not in series with only one of them, it's in series with both of them. So we have to combine these two first because they're in parallel. So if we do that, it's going to be 2.4 times 3 over 2.4 plus 3, which gets us 1.33. So then we'll have A and B, 2 ohms, 1.33 ohms. And then if we add those together, right, we'll end up getting that the total equivalent is 3.33, which is just 1.33 plus 2. And that would be our RTH. Then you combine both of these again in the same way, and you will get a 4.22 volts here and a 3.33 ohms at A and B. And that's your final answer. Okay. I have time for maybe one more question. Let me find one that I think looks good. Hmm. I might actually just end it here. I did 2 questions for each topic. I think that's pretty good. So, yeah, I'll do like one more brief mesh current one because that's something that I kind of want to drive home. But this one shouldn't be too long at all. Okay. So this is here, and it's right, all equations to find Ix, mesh current. So again, we have our 3 loops. I'll call this one I1, this one I2, this one I3. And we just have to write our equations. We'll have 3 equations and then 1 equation defining what Ix actually is. So for I1, starting with that 2 ohm resistor, since that is just connected to that I1 loop, it's just going to be 2 times I1. The 3 ohm resistor, it's on the border of 2 of them, so it's going to be 3 times I1 minus I3. And then the 2 ohm resistor, it's 2 times I1 minus I2. And then that 48 volt source, since the voltage drop is in the direction of I1, it is positive here, so it's plus 48 volts equals 0. For I2, we're going to start with that voltage source. Now it's going to be in the other direction, so it's negative. Same with that 2 ohm resistor. Now it's going to be 2 times I2 minus I1 instead of I1 minus I2. And then for the 6 ohm resistor, it's going to be 6 times I2 minus I3. And that's everything for that loop. And then for I3, for I3, actually, we don't have to do anything because there's a current source. It just tells us. Same as before, since the current source is kind of facing the opposite direction as the loop, it's just going to be negative 4 amps, right? And then last but not least, we have to say the dependent source. So Ix, if we look at this, okay, it is Ix is defined as going that way. We have I2 going this way, and I3 is going the other way, right? Because it goes like that. So if we're looking for an Ix in this direction, and I2 is like this, and I3 is like this, then Ix is going to be equal to I2 minus I3, just based on the direction of those arrows. And then this would be your final answer with those 4 equations. If you were to plug all those in to your favorite equation solver, then that would give you your Ix. And yeah, hopefully that's good. Hopefully you guys understood and can implement this on your quiz tomorrow. Some things I will re-emphasize. These points always make all the currents go in the same direction. It'll make your life easier just because if nothing else, you can always have like these terms in the first, depending on which loop you're doing. So like if you're looking at the I2 loop, you're always going to have I2 in that first term. If you're looking at the I3 loop, always have I3 in the first term. And like between loops, you'll have this versus the opposite in this loop. And that just makes everything work a lot nicer. Um, then also this is a big point. People get tripped up by this a lot. If you see a current source, then it is directly telling you what the current is. So you can't make a KVL equation with the current source. You don't know its voltage, but it does tell you the current. So if you're doing a loop and the loop is you're trying to find like I4, but it's telling you what the current is, then it's telling you what I4 is. So try to get that through your head. And then last but not least, try to remember this. This is just an easy way for me to remember it. A wire, there's no voltage difference across a wire. Everywhere on the wire has the same voltage, so it has no difference. That's why it is the opposite of a voltage source. Whereas for a current, if you want to get rid of a current source, that means there's no more current. So no more current means it's an open circuit. And yeah, so that's a key thing as well. And yeah, with that, I will end the recording and good luck on your quiz tomorrow. Bye bye.